In this video, we want to see how we can implement a consistency protocol, a data consistency protocol with DKVf. So to implement a protocol with DKVf, we need to take 4 steps. So the first step is to create a metadata class. So this class describes our record structure and the client message and server message. Okay, so for the metadata class, DKVf relies on Google Protocol Buffer. So what we need is to write a proto file that describes our record, client message, and server message. The second step is to write a record comparator for the storage engine. So basically, this function defines the order of different versions for a key. Okay, so we consider multi-version. Using DKVf, you can design single version or multi-version databases. But if you are designing a multi-version, then using a record comparator, you can specify which of them is most recent. Okay. The third step is to write the server side of the protocol, and the fourth step is to write the client side of the protocol. So let's begin with creating the metadata class. But before going to that part, let's consider what system we consider in this video. So DKVf is mainly designed to create distributed key value stores. So in a key value store, our data items are key value pairs. Okay, so we have a pair that has key and value. We can access the value by the key. So we consider a replicated data store where we have a set of key value store which is replicated in different location. So for example, in this figure we have 3 replica R0, R1, and R2. So each of them has a full copy of our key value. Each of them has the full copy of the key space. Okay. It is not a requirement for DKVf. You can design a system for partially replicated system, but for this video we considered a fully replicated, eventually consistent distributed data store. So in eventual consistency, the only guarantee that we have is that finally all replica converge to the same set of key value store. Okay, so it is possible that for some time one of the replica has a value that the other replica doesn't have it, but if we stop writing to the data store and if the replicas are connected with each other, it is guaranteed that finally all of them converge to the same set of key value stores. Okay, so to converge different version for the same key, we use last right wins policy. So in this policy we define a recency for versions. So we define when a version when a version is more recent than the other version, and then we provide the most recent version. So in this video we use timestamp to define the order of the version. So if you have 2 different versions for the same key, the winner version is the one with the higher timestamp. For example, in this figure we have 2 versions. One of them has timestamp 3, the other has timestamp 2. So the winner is the version with timestamp 3. So if we have 2 versions that have the same timestamp, we use the replication ID. So the version with the higher replication ID is the winner version. Okay, so using this policy and by sending replicate message between replica, we guarantee that all replica will converge to the same set of key value pairs. So when we define the metadata for our protocol, we need to define 3 elements. Okay, the first element is the record. So it talks about what is the structure of an individual object that we want to store in a memory and later in a disk. And the second one is the client message. So what is the format of a client message? And the last one, the server message. So we consider each of them one by one, and we see how we can write the corresponding protocol buffer description. So let's start with the record. So for each record, so we have a key, and for the value part of the key we have a byte array. We also need to store timestamp, which is we use int 64-bit, which is like long in Java, and we store a source replica ID, which is a int 32 bits. So now let's see how we can write the corresponding proto description for it. All right, let me start writing the proto files. So I first create a working directory in my desktop. I call it eventual consistency with DKVf. So I create a text file. I call it eventual proto. So I use Notepad++ to write my proto file, but you can use any editor that you want. So the first 4 lines of my proto files is the same for any protocol that you want to implement with DKVf. So the first line specify for protocol buffer which syntax we are using. So I'm using version 3, so proto 3, but you can use later version 2. And for the package I use package metadata. Okay, I define an option which specifies my Java package. Note that these lines should be exactly the same for any implementation, so you have to use this Java package, edu.msu.cse.dkvf.metadata. Okay, option Java outer class name method. So this is the name of the class that protocol buffer wants creates for us. Okay, so I want to first create my describe what is my record. So to describe any element in protocol buffer we use a message block. Okay, so it's like a struct or class in object-oriented languages. So I define record. So your record should exactly have this name, record with capital R. Okay, so as I said, we have each record. We don't include the key in the record. It should be the value part. So it has a byte array. We use bytes for byte array for the value. We assign a tag. The tag should be positive integer, so I start with 1. I use the int 64 for my update time, and use an int 32 bits for my source replica. All right, so this is my record. Okay, next we want to focus on client message and the server message. So for client messages, we have 2 types of client message. The one is the get message and the other is a put message. So get message is used when the client wants to read a value, the value of a key. So it has only one element, which is the key, which is a string. The other message is the put message and is used when the client wants to read a value for a key. So it has 2 elements, a key which is a string and a value which is a byte array. So corresponding to these client messages, we have client reply messages that we also have to define for our proto file. so which are the get reply that has only the value that the client asked for, and the put reply has two elements which are timestamp and source reply. They are not necessary for an eventually consistent data store, but I have included for sake of presentation in this video. So let's see how we can write the corresponding proto file or proto description for our client message. So the first message type is the get message, right? So I create a message for get message, and so get message has only a key, so I assign the tag 1. I also need to define put message. Alright, so for put I have a string key and bytes value 2, right? So you know, the get message and put message are not required by the DKVf, so you could use any other name, but the DKVf require to have a message block with name client message. Okay, so I define that client message. So the client message is representing the format of my client message. So a client message in my example can be two. It can be get message or put message. So I use one of keyword and specify define a member called message type, and it can be either get message or it can be a put message. Okay, so as we can see here, so my client message can be either a get message or a put message, and so I have defined get message and put message here for that. So I need to define reply message too. So I define message get reply, which has a byte array, right? And also put reply, which has int 64 UT and int 32 S, right? So the same as client message, DKVf require to have a block for message client reply. Okay, so for client reply I can define anything. So I define a boolean to show my status. So it the boolean shows if the operation has been successful or not, and then I use one of again, and I can define get reply, okay, to, or a put reply. Okay, so I'm done with the client part. So this is all I have. Oh, there is an error. I should have an equal sign here. Okay, so I'm done with my record and the client message. So DKVf require to have a record block, client message block, and the client reply. These are these are messages that I define for myself and I use in the mandatory messages. Okay, now we want to see how we what are the server messages. So for the server message, we have only one type of message in this system, which is the replicate message. So basically whenever there is an update in one of the replica, that replica needs to send a replicate message to other replica to inform them about the update. Okay, so each replicate message has a key which is specify the key that has been updated, and a member of type record, which is the same type that we define for our record structure. So it includes the value, timestamp, and the source replica ID. So I can directly create a server message block, but to have a clear description that is close to my client message, I define a message block called replicate message. So it has a string key and a record rec. Okay, this is my replicate message. Now I define my mandatory message, which is server message. Okay. And so I say that I have a member of the replicate message, which is called replicate message with tag. Alright, so this is our Porto description for our eventually consistent data store. Okay, now let's see how we can compile this .porto file to have our necessary Java class. Okay, to do that you need to download the Google Protocol Buffer compiler. I have downloaded the binary, so let me extract. So I copy my, you can address, but I do this just simpler. So I open the command prompt. Okay, so I simply call the protocol buffer compiler with my Porto file, and I use Java _out current folder. So it's very quickly compiled that, and it has created the package. So basically it has metadata.java that has the whole code. So thanks to Google Protocol Buffer, you have the code, the necessary code for serializing and deserializing data over for your storage in the Berkeley DB or any other storage, or even sending and receiving on the network. So you have the necessary Java file for it.